Dear students, in the last lecture we have discussed about nearly free electron model, and we have discussed that this model could be used for distinguishing between metals, semi-metals and semiconductors by introducing the concept of energy bands. Okay. And in this lecture we are looking at a model, a nearly free electron model. In the nearly free electron model, electrons used to interact with the potential, periodic potential in the lattice provided by the ion cores in the lattice. Okay. So, here we assume a model in which the electrons are moving in a periodic potential. So, this model is called Kronig Penney model. In this model, when you have in a lattice, you have a periodic arrangement of positive ion cores, and the free electrons are the electrons which is provided by the conduction electrons in the material. Okay. And when these free electrons move inside the crystal, electrons will be suffering from periodic potential provided by the ion cores. And the potential at the positive core is very small, and the potential will be very high in the intermediate in the region between the two ion cores. Okay. So, if you draw a graph between the potential versus distance, and you can see at the position of positive ion core, the potential is minimum and it is maximum in the position where in between the two ion cores. Okay. And this is repeating because the ion cores are periodically arranged in the lattice. Okay. And now if you want to solve this model, you have to write down the Schrodinger equation, and the Schrodinger equation will be having the potential term V term. And in the free electron model, we took V to be 0 because we neglected the interaction of the electron with the periodic potential. Okay. And we have here some potential which is 0 at the positive ion core and maximum at the regions between the in between the two ion cores. Okay. But if you model this as a triangular wave or something like that, then the situation is very complicated, and solving the Schrodinger equation will be very tedious. Okay. So, what we do here is we approximate this potential to be a square wave potential, and you know how to solve a square wave potential. You have done this a couple of times when you deal with the quantum mechanics as well as in your BSc class also. Okay. So, what I do here is I took 0 potential in the regions near the positive ion core and a constant potential in the regions in between the two positive ion core. Okay. And this repeats. So, finally, what you get is a square wave. Okay. Square wave kind of potential. Okay. Square potential, periodic square potential. And in the realistic scenario, you can see the potential looks like something like this given in the figure. At the center of ion core, the potential is some negative potential, you can see, and in between the regions you have a 0 potential. Okay. And this is something called a periodic potential. Okay. So, we treat the electrons moving in a periodic potential, and you can use the periodic boundary condition. So, that gives you the wave function at any point x is same as the wave function which is displaced by the lattice constant A. Okay. So, നമുക്കൊരു wave function ഉണ്ടെന്ന് വിചാരിക്കുക psi of x at any point. Suppose ഈ ഒരു പോയിന്റിലാണ്, ഈ ഒരു പോയിന്റിൽ നിന്ന് a ഡിസ്റ്റൻസിലുള്ള ഏതൊരു പോയിന്റിലും വേവ് ഫംഗ്ഷൻ ഒരേ വാല്യൂ ആയിരിക്കും ഉണ്ടാകും. ഓക്കെ. ദാറ്റ് ഈസ് കോൾഡ് പീരിയോഡിക് വേവ് ഫംഗ്ഷൻ. ഓക്കെ. Now, the potential what you write down here, it is potential is 0 in the region 0 less than x less than a. Okay. That is called a region 1. Okay. So, I assume at the center is there is a positive ion core. So, the potential is minimum at there, and it is 0 up to a regime 0 to a. Okay. So, 0 to A the potential is 0, and from A to A plus B, so that is the maximum potential regime. I have some potential which is u 0. Okay. So, that is we can write on it as you take this region, okay, or this region minus b to x less than minus b to 0, that is region 2. Okay. Now, what you have to do is you have to solve the Schrodinger equation using this potential, okay, and this potential is repeating. Okay. Now, so you look at the Schrodinger equation. Okay. So, you have to split the regions, different regions we have. In the region 1 we do not have any potential, the potential is 0. So, this is free electron model kind of solution we will get. Okay. So, this is minus h cross square by 2 m d square psi by dx square times energy. Energy is completely kinetic energy. Okay. There is no potential energy. Now, we can simplify this expression and write in terms of some parameter called alpha, where alpha is 2 m epsilon by h cross square. Okay. As epsilon is the total energy in region 1. Okay. And in region 2 you have kinetic energy part as well as the potential energy part. Okay. So, in this region I am introducing a parameter beta, which you can write down as minus 2 m by h cross square epsilon minus u 0 u 0. Now, you know that so we have solutions in different regimes, okay, region 1 and region 2, but according to Bloch theorem, if you have a periodic potential, you know that the wave function should be of this form. It should be a it should contain two parts. One is a plane wave part, e raised to I k x, and there is a function which is periodic in space or periodic with respect to lattice constant. Okay. So, plane wave in the amplitude there is a space modulation, and that space modulation is periodic in space, okay, in lattice constant A. Okay. So, u k satisfies the periodic boundary conditions. Okay. So, this is according to Bloch theorem. Now, let us look at the solution of Schrodinger equation in region 1, that is this region, and region 2, that is this region. Okay. And you know, in region 1 this same as a electron as a free particle, and you will be having a plane wave solution. Okay. So, there is a forward moving plane wave and a backward moving plane wave. Okay. So, that is the solution in this region 1, and for this the epsilon energy you can write down as h cross square k square by 2 m. Remember, this k is not the k in the Bloch solution. Okay. So, this is for particularly for region 1. So, this wave vector k is particularly for region 1. Now, in region 2 that is a constant potential region. Okay. So, there you can have a solution of this form. Okay. I hope you know how to find out the solution for a constant potential. Okay. And this is of this form, where q is defined as u 0 minus epsilon equal to h cross square q square by 2 m. Okay. So, the wave number in this region is slightly different, which is given by q. Okay. And so, this is a familiar form you can get as q is equal to 2 m by h cross square, okay, into u 0 minus epsilon. You must be knowing this familiar form. So, this is q square. Okay. And you know, by Bloch theorem, the solution in region in this region, that is region between A and A plus B, should be related to the solution in the region B to 0. Okay. And so these two solution must be connected by the Bloch theorem. So, how do you write it? So, this psi is the solution in this region A to A plus B. So, that is equal to solution. So, this is the function of the form uk of x. Okay. And so this is the solution in the region between minus b to 0, and there should be a plane wave solution which is e raised to I k a plus b. Okay. So the two solution must be connected by the block theorem. Okay. Now you look at the so there are so many constants here, a, b and c, d. So how do you fix this constant? By using the boundary condition. So what are the boundary condition? Boundary condition usually we do, so you have to connect the two solution, the solutions in region 2 and solution region 1. So these are connected at the boundary by the boundary condition. So we impose that the wave functions are continuous at the boundary, and its first derivative is also continuous at the boundary. So at x equal to 0 and x equal to a. Okay. So there are two boundaries, one at x equal to 0 and one at x equal to a. The solutions are continuous. Okay. So the wave function itself and the derivative of the wave function should be continuous. And if you apply this boundary condition, you know how to apply this boundary condition, you will obtain a plus b equal to c plus d. So what you have to do is you take the wave function at region 1 and take the wave function to region 2 and put x equal to 0 in the two wave function, and this two wave function must be equal. Then you will get this equation. And also you take the first derivative of the wave function in region 2 and first derivative of the wave function in region 1. Then you insert x equal to 0, then you will arrive at this equation. Okay. And similarly at x equal to a, you will get these two boundary conditions. So you have 4 equations and you can solve them to find out the coefficient. And so how do you find out? Since there are 4 equations, it becomes very tedious. Okay. So you use the matrix method, and so you generate a 4 by 4 matrix. Okay. And let the matrix be called as T, and you have coefficients a, b, c and d, and you need to find out these coefficients. Okay. That is equal to 0, and this equation will be having solution only when the determinant of t is 0. Okay. Non-trivial solution exists only when the determinant of t is 0, and you can work it out. It is a tedious process, but you can still derive this equation. You will arrive at this equation. Okay. So this equation gives you the connection between the wave vectors in two regimes, k and q, and small k is the index which is labeling the block functions. Okay. It is a actual wave vector. Okay. Now it is difficult to proceed in this way. So we come to a dead end, but we can play smart. What you can do is you assume the thickness of b. I mean this is the region which is having thickness b, and you assume this thickness is tends to 0. So if that thickness tends to 0, I mean then it can be approximated as a delta function, provided u0 is infinity. Okay. This height is infinity. So there are two assumptions, thickness is 0 and height also increases. So in this limit the potential looks like a delta function. Okay. So it is a periodic delta function. Okay. So you can find out the solution in this limit. So in this limit looks very simple. So you do by this argument, these two arguments, b tends to 0 and u tends to infinity, and also you fix q square b a by 2 as a finite quantity, that is we put as p. Okay. This remains finite. Okay. Now you have to apply these limits, b equal to 0 and u equal to infinity, u0 equal to infinity. So in this limit q is very much greater than capital K, and qb is very much less than 1, because b is tending to 0. Okay. So, in this limit, so we are doing by keeping this quantity a finite constant, which is we call it as p. Okay. So, how does this terms modify? Let us take the first term. Okay. So, sin h qb will be approximately qb, and in the first term you neglect about this term because q square is very much greater than k. So, you neglect this term, okay, and 1 q we can cancel here, okay, and you can introduce a in the numerator and denominator, and q square ba by 2 which you put as p, and in the denominator you have a capital K a, and in the numerator you have a sin k a. Okay. So, in the second quantities cos h qb for a very small qb, this is 1, and you can write down cos k a. So, similarly this I can do in the right hand side b equal to 0. So, that is cos k a. So, you should remember this case are capital case and these are small case. Okay. And so, this is the condition you finally obtain for a periodic delta kind of potential limit. Okay. Now, here you plot the left hand side of this equation as a function of k. Okay. And this structure look like a sinc function. Sinc function, you know, it is a function which is sin k a by k a form. Okay. So, this you might have seen in some diffraction pattern, this kind of central maximum, and there is side bands which is dying out. Okay. And here the allowed values of k are limited by the energy. Okay. So, energy has some have some expression and which provides a limit on the value of k. Okay. So, k can take values 2 m e by h cross square raised to half in times a. Okay. So, these are the allowed. So, this you can derive actually from the energy expression E is equal to h cross square by h cross square k square by 2 m. Okay. So, if you put this limit, the allowed values are those values for which k lies between plus or minus 1, for which the function, not the k value, the value of the function lies between plus or minus 1. So, that is this regime is the allowed values of k. Okay. And you can see, so this region is allowed, but when it comes to this point, up to this point the k values are not allowed. Here the k values are not allowed, k values are not allowed in the shaded region. Okay. Here the k values are not allowed. Okay. So, there are gaps in the energy. Okay. So, this is basically the energy itself. Okay. In the, even though we have plotted the left hand side of this equation, this effectively gives you the energy. Okay. And there are certain gaps in the values of k for which there is no block like solution. So, ഈ ഷെയ്ഡ് ചെയ്തിരിക്കുന്ന ഭാഗത്ത് ബ്ലോക്ക് ലൈക്ക് സൊല്യൂഷൻസ് ഇല്ല, അതുകൊണ്ട് തന്നെ ആ സൊല്യൂഷൻസ് എക്സിസ്റ്റ് ചെയ്യില്ല. സോ, ഇതിന് കറസ്പോണ്ടിങ് ആയിട്ടുള്ള എനർജി സ്പെക്ട്രത്തിൽ ആബ്സെൻ്റ് ആയിരിക്കും. സോ, ദാറ്റ് മീൻസ് ദീസ് റീജിയൻസ് ആർ ദി energy gaps observed in the material. Okay. Now, if you particularly plot the energy in terms of k, you can see there are gaps, okay, energy gaps in the boundary. So, Brillouin zone boundaries basically. Okay. So, this function is plotted for 3 pi by 2, and here also this plot is also plotted for p equal to 3 pi by 2. Okay. And നമ്മൾ പറഞ്ഞിട്ടുണ്ടായിരുന്നു p എന്നുള്ളത് ക്വാണ്ടിറ്റി ദാറ്റ് ഈസ് q സ്ക്വയർ ബി എ ബൈ 2 എന്നുള്ളത് ഒരു ഫിക്സഡ് ആക്കി വെച്ചിട്ടാണ് നമ്മൾ ചെയ്യുന്നത് എന്ന് പറഞ്ഞു. സോ ദാറ്റ് ക്വാണ്ടിറ്റി വി ടേക്ക് ഇറ്റ് ആസ് 3 pi by 2. സോ അങ്ങനെ വരുന്ന സമയത്ത് എനർജി വേഴ്സസ് കെയുടെ പ്ലോട്ട് വരയ്ക്കുന്ന സമയത്ത് ദർ ആർ ഗ്യാപ്സ് ഇൻ ദി എനർജി. ഓക്കെ. സോ ദീസ് ആർ ദി ഗ്യാപ്സ് ഇൻ ദി എനർജി, ആൻഡ് ദിസ് ഗ്യാപ്സ് ഒക്കേഴ്സ് അറ്റ് ദി സോൺ ബൗണ്ടറീസ്. ഓക്കെ. k equal to pi, 2 pi, 3 pi, that means k equal to pi by a, 2 pi by a, 3 pi by a എന്നുള്ള സോൺ ബൗണ്ടറീസിലാണ് ഈ ഗ്യാപ്സ് അനുഭവപ്പെടുന്നത്. ആൻഡ് യു നോ ദ റീസൺ ഫോർ ദിസ് ഗ്യാപ്പ്. ഗ്യാപ്പ് ഉണ്ടാകാനുള്ള ഒരു കാര്യം എന്ന് പറയുന്നത് ദർ ഇസ് നോ ബ്ലോക്ക് ലൈക്ക് സൊല്യൂഷൻ അറ്റ് ദി സോൺ ബൗണ്ടറീസ്. ഓക്കെ. ദർ ഈസ് നമ്മൾ നിയർലി ഫ്രീ ഇലക്ട്രോൺ മോഡൽസ് പറഞ്ഞ സമയത്ത് പറഞ്ഞിട്ടുണ്ടായിരുന്നു അവിടെ പ്രൊപ്പഗേറ്റിംഗ് വേവ് സൊല്യൂഷൻസ് ഇല്ല, ദർ ഈസ് ഓൺലി സ്റ്റാൻഡിംഗ് വേവ് പാറ്റേൺസ്. ഓക്കെ, and there are two kinds of standing wave patterns that may create the energy gap. Okay, so this is an explanation for the formation of energy gaps in materials. Okay, so this is according to the Kronig Penney model. So in this model, it is important to derive the Kronig Penney condition and explanation of this graph, and this graph gives you how the energy gaps are formed in materials. So in the next lecture, we will talk about the wave function of electron in the periodic potential. Okay. Hope you understood the video. Thank you.